We looked at one of your parts this morning and looked at a toolpath issue on it, but we can't make a video of your part, so I've got a couple of parts here that we can use to kind of simulate the same sort of situation that we had with your part. And you have these parts as well, so go ahead and open up the radial lace cut part. Radial lace cut, .vnc, and this part has an island here in the middle, and this is not flat. It is, I believe it's just spherical. Yes, a spherical radius, and the edges here, and here are not parallel. So it's roughly wedge shaped. So I wanted to look for just a minute at programming this, and with your part it was important that the tool not run off, that the tool path here be parallel to this edge and here be parallel to this edge. Now with the 5-axis module, this would be very easy to do. You could also do this using an in-curve flow, but an in-curve flow in the advanced 3D can be a little more difficult to get it to perform the way that you want it to than the way that I'm going to show you. We can't use a 2-curve flow here because the 2-curve flow under surfacing essentially creates a line end point for each stroke from the end of this geometry to the end of the geometry down here. So it would miss out on the end of this, or else you would have to wrap it around that radius, which is obviously not what you were looking for on your part. So let's take a look at this. The main thing that I want to do here, or the first thing I want to do here, is find the focal point. Find the focal point, or what I call the focal point of this edge and this edge, because we want our toolpath running parallel here and then kind of morphing until it's running parallel here. And all we're doing is finishing this top surface. There's a couple of different ways to do this. I think what I'm going to do is just grab that edge and that edge, and I'm going to just extract those. Zero tolerance is fine. I'm not really looking for geometry here. Really all I wanted is those 2 points at the end of each line. So I'm going to delete the arc in between them. All right, so with that done, with my geometry palette open, I'm going to draw a line through these 2 points and through these 2 points. And then I'm going to connect these 2 lines. Sorry, I'm having trouble selecting today. So if I connect those, I get a point where those 2 lines intersect. All right, so, and just to reiterate for the video, a normal linear lace cut does not work for you in this situation, because if we made it parallel to this edge, when we get to this edge, the tool path would be running where it is dropping off or ending at the edge here rather than following this edge full length, and you needed a tool path that was parallel to this edge but also parallel to this edge. So the focal point of these 2 edges is this point right here. All right, so let me open up my tools, and I've got a 1/4 inch ball mill made up here. I'm going to do an advanced 3D toolpath with it, and I'm going to set this to lace cut. Now we've already gone over the raster style lace cut in some detail, but in addition to the raster, which is just linear back and forth following the surface underneath it with parallel strokes at whatever angle, whatever cut angle you set, we can also do a radial lace cut, which starts at a known center point and does kind of a fan-shaped tool path. and as well as a spiral lace cut. We're going to do both the radial and the spiral, but we're not going to do it like most every video does, which is going full circle. These are handy if you're lucky enough to have that situation, but they're also handy in a lot of other cases that are sometimes not always shown, not always obvious. So what we're going to do here is a radial lace cut. Now let me zoom out just a little bit, move this over so we can get to everything. And I want to go to my advanced settings. So the center of my fan-shaped toolpath, or my radial toolpath, just going to click in here. I'm going to hold down Shift Alt and click on that point. So this is going to be the center of my radial cut. All right, 0 to 360. I don't have to worry about this. Now, if I knew the exact angles here, I could set that if I wanted to, but I'm just going to let it look, full circle around that point. Now, this is important on a radial lace cut. The minimum 0 is fine, but the maximum of 10 inches means that my step over, whatever I tell it my step over is going to be calculated at that 10-inch radius. So at smaller radiuses, the step over is going to be much finer than what I have programmed here, because we're going all the way from a 10-inch radius down to 0. So at 0, it would be virtually infinitely dense. The toolpath would be. So what I could do, I could measure this if I wanted to. I could come down to view and just show mouse position and just move over here and kind of get a feel for where that's at. That's roughly at x2.5, y 1.3, somewhere in that area. So I should be able to go to 2.5 or 3 inch, let's just say a 3-inch maximum radius. And I'm going to set a step over of, say, 8 thousandths. I'm going to select what I want to cut, and top of the part at 0, and the bottom of the part doesn't really matter. I'm going to hold Alt down and just select the floor of this. That's fine. I could also Alt select the lowest point on that surface if I wanted to. And I'm going to go back and forth. But here's the neat thing. Even though we said that we're going 360 degrees, remember your toolpath is constrained by your boundary. We've talked about this already, but let's just run back through a couple of these again. Part bounding box is not a bounding box around your entire part. It's a bounding box around the selected faces. So if I selected this, you could essentially imagine a rectangle drawn or just brought in until the edges touch the yellow faces here, the selected faces, and that would be the area that toolpath is going to be calculated in. Stock bounding box is essentially the same thing around your stock definition. So whatever your stock definition is, you would have a bounding box drawn in around that. In this case, we're going to use silhouette. Silhouette means the actual outline of the selected faces. Now, if I were to hit do it now, I would not get any toolpath, and I know this because it is using I have a solid model for my stock, and just as a side note, the solid model has no material on this face. So that if it would calculate material only, even though rest material is unchecked, it's still going to base my toolpath on what is there to be cut, and there's nothing there to be cut. So I'm going to turn this to none and just have it calculate. Let's take a look at our toolpath. So it is calculating. This computer is not quite as fast as the one that I used yesterday. So we may have to sit here for a few seconds and let this calculate. I'm going to move this out of the way. And also the fact that we're recording video consumes some of the resources, so it's even slower than normal. All right, so here's the toolpath that we got. And if you'll notice, I should have done a bigger step over for demonstration purposes, but we're exactly parallel to this edge here and exactly parallel to that edge there. You can see our step over is slightly bigger out here than it is down here. because of the fan shape of the toolpath. But this is the way that I created a good toolpath on your part, where we had a fan shape 3D surface, and you needed the toolpath to be parallel to this edge, or parallel to one edge at the start and another edge at the end. Just to clean this thing up slightly and kind of finish what we did earlier, I'm going to go back to my surface tab, and I'm going to make the step over a little bit bigger just for the sake of speed. Actually, let's go ahead and go to 20 thousandths. And now, of course, on your part, we left it with a fine step over because you needed a pretty good surface finish. But we also reduced these entry-exit moves. These entry-exit moves are a little on the big side. So I'm going to come into these. I still want the both entry and exit, but I'm just going to divide that by 4 and divide that by 4 and divide that by 4. So I'm going to 1/4 of the default entry-exit. And hopefully this will calculate a little bit quicker. I could also have loosened up my tolerances a little bit and have it calculate quicker. So remember, while this thing's calculating, I can talk about a couple more things. Remember that your surface finish is controlled by your step over, obviously your actual toolpath selection, but your step over controls the smoothness between strokes. So it kind of your overall surface finish, your overall ridge height. But it is also your cutting tolerance comes into play here as well. This is spline toolpath, and by having a 1/1000th tolerance, we're basically saying that the spline toolpath can deviate from the model by this amount. So let's look at just a couple of other things here. I'm going to go ahead and bump that up to 30 thousandths, and I'm going to bump this up to 10 thousandths, and we're going to recalculate. So this would be a very rough surface finish, both because of a 30 thousandth step over with a 1/4 inch ball mill and because of a 10 thousandths cutting tolerance, but it should calculate significantly quicker. Now, to kind of illustrate what I'm talking about as far as the cutting tolerance go, since this finishes, all right, so here's our toolpath. So what I'm going to do is I'm going to create a new work group. And in this work group, I'm going to create geometry out of this toolpath. So I'm going to right click on the operation and say operation to geometry. All right, now this is fitting. I do have, I believe, yeah, fit arc. So we are getting some arc moves in here. So this actually is not going to be all that bad. But you see how, how few pieces of geometry along the stroke were created. I'm going to uncheck fit arcs, and the fit arc still had a tolerance of 1/1000ths. So let me get rid of this this geometry. So let me get rid of that geometry, and I'm going to regenerate this with fit arcs turned off. So we go back to options and uncheck fit arcs and redo. And this should speed up the toolpath as well, having fit arcs turned off. All right, so we got a 30 thousandth step over, a 10 thousandths cutting tolerance, as we are no longer fitting arcs into our toolpath. we'll give this just another few seconds to finish calculating. And we will convert that to geometry. Okay, so you can kind of think of each segment of this geometry as being a line of code. And you can see it's fairly sparse. There are long sections here that are essentially one line of code, one move of the toolpath. So you can see that the toolpath is what I would call coarse. This is not going to be a good surface finish. You're going to have a fair bit of faceting on 3D surfaces with a coarse tolerance. Of course, you wouldn't machine anything finished at a 10,000th tolerance anyway. But if I drop that down to a 1,000th tolerance, and let's just get rid of this, reselect that, 1,000th tolerance still with fit arcs turned off, and we'll recalculate that one more time. I just want to show you the difference in how much toolpath is created, how closely the toolpath, or let me rephrase that, how much more toolpath is created in order to keep the tool closer to the actual surface with a finer cutting tolerance. Now, on close tolerance parts where you need a very good surface finish, 1,000ths may not be close enough. You may cut that down to, half thousandths or a couple of tenths. And of course, you end up with a longer program at the machine. That's not an issue with most newer machines, certainly not with yours. But let's just take a look at this, and you see how many more pieces of geometry are created here, how many more lines of code to keep that toolpath closer to the actual surface. So your surface finish is controlled by your step over. In this case, it's also controlled by your cutting tolerance. The step over again is more side to side, if you will. The cutting tolerance is more along the strokes, how close your toolpath is going to match the solid, and how smooth the transitions are. So if you're seeing unacceptable facets, they would be going across this way. You'd see a flat here, a flat here, a flat here. If you see that sort of thing, and that is the part of the toolpath that is not acceptable, then improve your cutting tolerance. The other thing that you can do on that is to fit arcs. Now with fit arcs, my strategy is kind of the opposite. Here, going to a smaller cutting tolerance improves your surface finish. On fit arcs, typically you want this to be a larger number where you can stand for the toolpath to deviate slightly, because the larger this number is, the fewer arcs are required to fit from here to the other end of the stroke and still keep it that close to the surface. So fit arcs will improve your surface finish. I typically use the tolerance here. I'm not going to let it deviate much from the surface on most parts, but thousandths or two, if you can stand it on your part, will increase your surface finish, will improve your surface finish significantly. All right, so let me go ahead and end this video, and we'll do a separate video for a spiral lace cut, which is the other toolpath that we did on your part.